Hello, my name is Oliver Mais and I head the Research and Development Department here at ECOROLL AG. Today I would like to give you a brief introduction on how load stress and residual stress can be superimposed. We'll do a small thought experiment to get a sense of why tensile stresses are negative and compressive stresses are positive for the service life of a component. Residual stresses are stresses within a component that exist even when no external forces, moments, or temperature gradients are applied. This means that a component still has residual stresses even when it's just lying here on the table in front of us. So if you have your shaft, your component, or your forming die lying here in front of you, there are residual stresses present in it. Residual stresses are introduced by every manufacturing process. Whether they are forming-induced residual stresses, machining-induced residual stresses, or stresses introduced by thermal or heat treatment, it doesn't matter. Of course, I can also subject my component to elaborate stress relief annealing afterwards to eliminate the residual stresses. But if I do it right, I can use residual stresses to extend the service life of my component. Our managing director has a wonderful example, and I found it so enlightening when I first heard it from him about how residual stresses have an effect. You can imagine if you have an eraser and you bend this eraser, then, as I've also shown in the picture here, at some point cracks will start to form on the surface. Cracks will inevitably develop, and if I continue bending this eraser repeatedly, it will certainly tear along this developing crack until it eventually breaks completely apart. And now we can do a thought experiment, the first one for today. We can also try squeezing this eraser a little bit. So that means you take the eraser and before you bend it, you squeeze it a bit. And even while you're bending it, you keep squeezing it more and more. And then you'll notice that the eraser will tear on the surface at a slightly later point. That means you can bend this eraser a bit further. And that's exactly what we want to achieve with compressive residual stress. We want to ensure that compressive stresses are present or contained in the component, which then essentially counteract crack propagation and crack initiation. That means residual stresses overlap with the applied stresses. My compressive stress, so what I just did with the eraser compressing it, simulates my compressive residual stress, and these overlap with the load stress from the bending. So compressive residual stresses have a positive effect on crack formation. They help ensure that cracks form later, and they also slow down the propagation of cracks once they have formed. This means that compressive residual stresses also have a significant impact in the dynamic range, and especially here, they act to increase dynamic strength. However, residual stresses also have a disadvantage in one respect. Since the sum of all residual stresses in an entire component must always be zero, in other words, every component is balanced, otherwise it would continuously move. So a component sits still in front of us on the table and doesn't move all the time. Residual stresses therefore tend to always balance themselves out, and they do this through deformation. This means that if I introduce residual stresses into my component, it will deform somewhere else. Now, from mechanics, we know a very simple relationship for superimposing load stresses. We can simply add them. We can simply add load stress and residual stress. This would be the case here, just load and residual stress, and then calculate a resulting stress. Here, I've just written down the very simple formula. Sigma res equals sigma load plus sigma residual stress. This is also valid as far as it goes. And if I now take a component and apply a uniaxial stress state to it, that is, I simply pull on my component, it's fixed to the wall on one side, and I just pull on it, then of course I have a uniaxial load stress in the component. With the formula I just mentioned, I can of course simply say, in a component that has no residual stress, the resulting stress is equal to the load stress. In this case, maybe 600 megapascals. Plus no residual stress, so plus 0 equals 600 MPa. A simple relationship. But now I can also take the other component and say, my component contains a compressive residual stress in the direction of the applied load. That means I can use the formula again and say the resulting sigma equals 600 MPa tensile load stress plus 200 megapascals compressive residual stress, so minus 200 megapascals. The resulting stress is then 400 megapascals. And with this simple example alone, I can show why compressive residual stress has a positive effect and tensile residual stress has a negative effect. Of course, I can also do all of this using the stress tensor. That means I can set up a stress tensor for my component, which has stresses in all directions. And in this stress tensor, I can again add the load and the residual stress in each individual stress element. I've simply illustrated that here on the right side, shown in a slightly more complicated way. In fact, here it's just sigma x plus the residual stress in the x direction for each individual element. Sigma y plus the residual stress in the y direction. And what effect does that have? I'd like to show that with a small example. For this, I've brought along a bending beam again. Admittedly, the bending beam is of course a uniaxial stress state. But the whole thing would also work if I had a multi-axial stress state. I can easily calculate the equivalent stress for this bending beam by taking the square root of 1.5 times, always sigma x minus sigma y squared, and so on. Calculate. But I can now say that for this bending beam case, I have no stress in the x or z direction. And in the y direction, I have a load-induced stress that results from the bending. Additionally, in this bending beam, I can also have residual stresses. These residual stresses are such that I have no residual stresses in the x direction. In the y direction, I have the axial residual stresses acting on my component. And in the z direction, I have the circumferential residual stresses acting there. And then with that, I can basically recalculate the equivalent stress using the stress tensor. And I would like to show how this affects things in a small diagram. The diagram shows the bending stress, that is the load stress, with which my bending beam is bent on the x-axis. And on the y-axis, I have always calculated the resulting equivalent stress. Now, of course, the gray curve here represents a very simple relationship. I have a uniaxial stress state, so bending stress is always equal to equivalent stress. And now I assume that my component has residual stress. I'll make two assumptions here. First, I assume that my component has the same residual stress in both directions, that is, in the circumferential direction and in the axial direction. And then I make the second assumption that, in one case, both stresses are 400 megapascals of tensile residual stress, and in the other case, each is 400 megapascals of compressive residual stress. The resulting equivalent stress without any additional bending stress is described here by the light blue curve. The light blue curve simply shows that my residual stresses are constant and that I always have 400 MPa in every component. So what happens if I additionally bend the component and only have the tensile residual stress case? Then I have, as shown here, at the zero position, meaning when I haven't applied any bending yet, I already have the existing 400 MPa equivalent stress. If I then apply an additional bending stress, it gets added on top. And so to speak, with increasing bending stress, I get more and more equivalent stress. That means a tensile residual stress increases the equivalent stress value. It gets interesting when I have compressive residual stress. With compressive residual stresses, in the case where I haven't applied any bending yet, so I'm all the way to the left in the diagram, I also have these 400 MPa equivalent stress simply due to the residual stress case. As the bending stress increases, this equivalent stress initially decreases and then approaches the 400 MPa again. And then, once the stress reaches 400 megapascals, I start to go higher again. And I'm above this 400 MPa threshold. But overall, I'm still below the equivalent stress without residual stress. So the dark blue curve runs lower than the gray curve. And this is essentially an effect of compressive residual stress. The compressive residual stresses reduce the equivalent stress and essentially counteract this bending stress, thereby reducing the equivalent stress in this case. With that, I thank you. I'm glad if you watch this video or any of my other videos. Like, share, discuss them with others from your company, and if you have any questions or comments, feel free to reach out to me or my colleagues at ECOROLL AG.